Nitration of benzene. We need benzene. The nitration mixture is nitric acid and sulfuric acid 1:1, and it will replace this hydrogen to an NO2, the electrophile. So that's how the simplest way to look at nitration of benzene. And we want to notice one thing: the quality of sulfuric. It is a catalyst, it's a dehydration agent, it's a water scavenger. And not only those qualities, we also use heat, and therefore that's also helping to remove the byproduct of water. Now, if you look at how to make the electrophile, you react sulfuric with 1 nitric, equimolar, 1 mole at a time, and then you're going to end up with 1 water molecule, NO2 plus the electrophile and the anion bisulfate. Now, so this electrophile, E plus, NO2 plus, you should think it is like R plus, acyl plus, if you remember the alkylation and acylation, the Friedel-Crafts, and it's the same style, same thing. I would not differentiate or different those 3 reactions. They are pretty much the same. Let's look at a little bit about the behavior of the 2 acids. Sulfuric is the stronger acid, and it will always be deprotonated the way I have shown. Now, what's the magic about nitric is a little bit weaker acid than sulfuric. Therefore, it's going to get the proton, so kind of behaving as a base. Now, so what happens here, it's an equilibrium. And in this equilibrium, sulfuric behaved as an acid, nitric behaved as a base and grabbed a proton. And so that proton I can show here in yellow. Now you have 2 positives next to each other. So this is not a good situation. That's why this lone pair comes in, remove a neutral water molecule. That's the driving force of formation of the electrophile. So if you do have to know the mechanistics of it, this is how you explain. Sulfuric is a stronger acid and it prepares the electrophile NO2 plus, and it's a linear ion. And the electron octet is completed in the central nitrogen, 4 bonds and positive charge. So that's what you want to know about the electrophile. So we are good with that mechanistic analysis, right? So we can look the details again. So here, benzene, then I always like to see which one is substituted the hydrogen in this case, and NO2 plus the electrophile will grab the nucleophile, the pi bond, will grab the electrophile, and then you're going to get this one. Because you lose an electron here, this carbon gets a positive, and the other carbon gets the hydrogen there still, and the NO2 is attached. Now, plus on the NO2 disappear because it got a pair of electrons to make the bond, right? Now, so you want to look at the details of this sigma complex, and it's no longer aromatic now. So now what happens? So we can move around this positive charge within the benzene nucleus, and the lone pair moves into the positive, and the positive moves into the next carbon here. Right? Now we have a new pi bond, the old pi bond, and the H and the NO2 as it is. Now we can move in the same direction again. So you try to move, always keep the older ones as it is, right? So this pair of electrons moved onto the positive. So the positive moves onto the top of the benzene, and then these 2 bonds appears, the pi bonds. Now you can use the bisulfate to extract this proton. The deprotonation takes place. 2 electrons fills the positive and makes a new pi bond. That's how you get this product here. So now we have the NO2 attached, and we have the created new pi bond. So that means aromaticity is re-established. But we can also show this resonance structures like that. Thank you.